I want to give you a little bit extra help with these binary, octal, and hexadecimal numbers. They're just different number systems. And, if you think of just our number system, which is decimal, okay, so our number system is decimal or base 10. That's our number system. So if you look at just any of our numbers, let's say we had 1,327. Well, for our number system, we have place values. Like, for instance, this right here is the 10 to the 0 or the ones place. Okay? This one right here is 10 to the first, or what we call the tens place. And as we move on, you should be seeing a pattern. Whoops. This one is 10 squared, which 10 squared is the hundreds place. And then this one here is 10 to the third, which is the thousands place. And we keep going, so on and so forth. Okay, we can, go to the 10,000s, the 100,000s, and so on and so forth. Okay, adjust this camera a little bit. And so when you're doing different number systems, it works very similar to our number system. Okay, so for example, if I'm doing binary, or what we know as base 2. So if you think about decimal and base 10, with each place value being a power of 10, well, binary is base 2 is each place value being a power of 2. And also, in our number system, base 10, you can never have a digit bigger than 9. So we have 0 to 9 for each place value. Well, in binary, you cannot have any digits bigger than 2. So that's why a binary number looks so funny, because it's all ones and zeros. Now, they use binary in a lot of computer type programming and in circuits for on-off switches, things like that. And so that's, if you just wanted to know, that's why they do this. But a binary number might look something like this. Okay, and they're going to put that little 2 down there just to tell you it is base 2. So, this place value right here is 2 to the 0, which again is your ones place. And we just kind of go on up the list. This is 2 to the first, or the twos place. This next one is 2 squared, or the fours place. 2 cubed, eighths place, so on and so forth. So this is 2 to the fourth, 2 to the fifth, and so on. Okay. Now, octal, or base 8, is where you're going to have same setup as we do for decimal, binary. The difference is now you can only have digits that go from 0 to 7. And if I had an octal number like this, that's base 8 again, subscript, then that is your 8 to the 0, or your ones place. Sorry about that, I forgot to write my 8 to the 0. This is 8 to the first, or the eighths place. And this right here is 8 squared, or the 64's place. And we can keep going. 8 cubed, 8 to the fourth, so on and so forth. Now, hexadecimal, a little different there. Well, not a little, it's different when we get to the letters, and I'll talk about that here shortly. But hexadecimal, or base 16, again, has the 16 to the 0, so they all have a ones place. This one here is 16 squared, 256 place, okay, so, or 16 to the first, sorry about that, 16s. Then your 16 squared, which is your 256. And I'm going to write these out just because it gets too long. 16 cubed stands for 4096. And all these numbers I'm writing here is what these would be in base 10 in our number system. Okay. And that's how we can convert, which I'm going to show you shortly. Now, the thing about hexadecimal, we can go from digits 0 to 15. The problem is, if you're trying to represent a digit of 13, you can't do that in one place, because then that all of a sudden looks like two different digits. So that's why they use letters. Okay, that's why they use the letters. That's why A represents 10, because see, 10 is two digits. So instead of writing a 10 in one of the places, because it would look like 1 and 0 in two different place values, we use the letter A. Okay, so that's kind of like an overview of what we're dealing with here. What we're dealing with is saying, if I have a number in binary, then I can get the representation of what that number is in decimal, because I've converted each place value to a decimal value. Okay, and let me show you what I'm talking about. So if I do have 11010 base 2, and I want to go to decimal, which again is base 10, well, this is the ones place, all right? This is the twos place, the fours place, the eights place, and the 16s place. So I have 116, I have 18, I don't have any fours, I have 1, 2, and I have 0, 1s. And that's what I'm doing. I'm multiplying here. But in theory, what I'm really doing is I'm just taking 16 plus 8 plus 2, because everything else is zeros. And that gives me 26 base 10. Okay? What you got to be careful with is not forgetting that this is a ones place. And then you increase, each time you're doubling. Okay? Powers of 2. All right? If I have binary, let's say I have 264 base, or an octal, excuse me, and I want to change that to decimal, again, which is base 10, and that's all that means there. That has no calculation value at all. It's just indicating what base we're dealing with, just like this 8 here. So again, I look at this number, and this is my ones place, this is my eights place, and this is my 64s place. So I have 2 64s plus 6 eights plus 4 ones. So that's 128 plus 48 plus 4, and that is 52 and 128, which is 180 base 10. Okay, so now let's look at a hexadecimal. All right, let's say we had 3AC2, and that's base 16. And let's change to decimal, which again is base 10. So this still is my ones place. This right here now is my 16s place. Remember, this is 16 squared, which is 256. And then this third place is 16 cubed, which is 4096. Okay. So 3 just represents 3. 2 still represents just 2. But A and C are those places where we have 2 digits. Like, for example, again, like I told you earlier, A actually represents 10. C represents 12. So what I have here is I have 3 4096s, plus I have 10 256s, then I have 12 16s, and I have 2 1s. So if I add all these together, I get 15,042 base 10. Okay, so the difference in the hexadecimal versus the other two is the letters. But again, you know, when you think about a base system, you're talking about place values and, you know, how many digits you can have. So binary, again, is just 1 or 0. That's all you can have in binary, 1 or 0. Octal, you can have 0 to 7, but you cannot have any 8s, because once you get to an 8, you have to go to a different place value. And hexadecimal, you can have 0 to 15, but the problem is you can't write, you know, I couldn't write 10 here for the A. That would look funny, because that would look like 310C2, which would look like I'm adding another place value. Okay, I know this is confusing, but you just need to practice. Okay, that's what will make it better. Trust me. Oh, those are the famous last words right there. Trust me. It will, though. It will. All right, so let's look at now, how do we convert from decimal to these other number systems? Okay, so let's go from, let's just say we have 78 base 10 to binary, which again, remember, binary is base 2. Now, I often in my on-campus classes, I show 2 different ways to do this. I will for binary, but really the second way I'm going to show you works for all 3 methods, because with binary only having a 0 or 1, it makes things a little simpler just to kind of piece things together. So let me show you what I'm talking about when I'm talking about piecing things together in binary. Okay, now just, you know, I make my little marks here. Okay, I've got my 1's place, my 2's place, my 4's place, my 8, my 16, my 32, and my 64. So I'm not going bigger than 64 because 78, you know, is close to 64. My next place would be 128, which is bigger. So I don't need that. So if I look at this, well, I've got 164 in 78. Okay, which means that 78 minus 64 is 14. So I don't have any 32s. I have no 16s. I have 1/8, because don't forget I still have 14 left over. And 14 minus 8 is 6. I have a 4, a 2, and a nothing. Okay, and that would be your binary answer, 1001110. Okay, that works easiest for binary, but for octal and hexadecimal, there's too many possibilities to really do that effectively. You know, you think about octal as base 8, you know, you could try 3, 4, 2. I mean, it would take forever. But binary, it's pretty simplified, because you either have 1 or none. And so you're dealing straight with the number itself, either being 1 or none of them, versus an octal, there could be 1, 2, 3, 4, 5, 6, 7 of them, and it would just take longer than doing it this second way. So here's the other way to convert. Okay, this is to convert by division. Okay, all right, so I'm going to convert by division. So I'm dividing by my base number at all times. So I take 78 divided by 2, and I get 39, and my remainder is 0. Now you'll notice 0, 0. Okay, just kind of keep that in mind. Now I take this number here and I divide by 2. Now when you're doing your divisions, you are only writing down whole numbers. You're not putting decimals in here. So sometimes you have to do your calculator a couple different times here, because 39 divided by 2, you're going to get 19.5. but you want to write down the 19, and then you got to take, well, 2 times 19 is 38, so that means my remainder is 1. And there's my 1, okay? And we repeat this process. 19 divided by 2 is 9. Again, remainder is 1, because for binary, your remainder is either none or 1. And I keep going. 9 divided by 2, 4 times. Remainder is 1, and you kind of see these 3 ones here in the 0. 3 ones and 0. All right, now 4 divided by 2 is 2. There's no remainder. 2 divided by 2 is 1. Still no remainder. And here's the key. 1 divided by 2 is nothing, and my remainder is 1. That's how you know when to stop. Okay, you know when to stop when you're at the end of the line where, the divisor does not go into this number anymore, and that's when you stop. And can write down the number, okay, this is your first digit in binary or any of the others, and this is your last digit. So make sure you list them properly. So it's 1 0 0 1 1 1 0, just like we have up here. Okay, so that's going from decimal to binary. Octal, it's just, again, it just gets more complicated with as far as, getting your remainders correct. Okay, so if I went, let's try, I don't want to make it too long because then, it's going to be forever, the process, but let's try 121 base 8, or excuse me, 121 base 10 to octal, which is my base 8, okay? So I'm taking 121 divided by 8. So if you're using your calculator here, I'm going to show you something here, okay? So you get 121 divided by 8. So that gives me 15.125. So I know this is 15. Okay, now I take 8 times 15 to get 120, which means my remainder is 1. Okay, so then I take 15 divided by 8, and 8 goes into 15 one time, and my remainder is 7. One divided by 8 is none, and my remainder is 1. So again, first digit, last digit. Not fist, but first digit. So it's 171 base 8. Now, if you want to check to make sure you're right or wrong, you have a 1. Again, you have your 8's place, and you have your 64's place. So you have 1 times 64 plus 8 times 7 plus 1 times 1. And that's 64 plus 56 plus 1 is 121. Okay? So that's how you can check that. All right, so let's look at now the hexadecimal conversion. Lots of paper today. These do take a while, okay? They do take a while. But once you get the process down, I think you're going to be okay. All right, so let's go with 1324 base 10 to hexadecimal, which is base 16, okay? So we take 1324 divided by 16. So I look at this. Now this is going to be even probably look worse on the calculator, but let's look at it. 1324 divided by 16 equals. So I get 82.75. Okay. Remember, I'm just writing down the 82. Now, how do I get my remainder? Well, I'll take 82 times 16, okay, which is 1312. And if you look at 1324 minus 1312, you get 12. So my remainder is 12. Okay. 82 divided by 16 goes 5, because 5 times 16 is 80. Remainder is 2. 5 divided by 16. 16 does not go into 5. So my remainder is 5. So that's again how I know how to stop. So look at how we've been doing things. So this is your first digit. But I'm not going to write down 5212. Because if I wrote down 5212, well, now I got 4 digits, and I don't want 4 digits. So instead of doing 5212, we do 52C, because C is the same as 12. Okay, that's why we have letters, because you do not want to have 2 digits in one place value. It would be confusing. Okay, so that's wrong there. All right. So that's what I got. The rest, you just need to practice it. Okay. And once you do, you'll get more comfortable. Just keep in mind the differences in the number systems is just basically the differences in place values. And some of you all that may not be in the program, as I stated the first video I made of this class, this is a class for people in the manufacturing, industrial maintenance programs. You do this type of stuff for your PLC classes, which are these programmable, I think, logic controllers. I don't even know what it's called, but it's kind of where you have all these switches on these assembly lines. And that's just how it works. And that's what they have to do. Okay, so you have to know this stuff for that. If you're just a regular math student using this for a prereq for college algebra, you got to suck it up and take it, because this class is for those students that need it for their program. Okay, but I'm confident you can do it. And nothing better, nothing beats practice. All right, so have a good one.